Welcome back to our series on applied regression analysis. I'm Mark Ledbetter. This is lecture video 49. We're in chapter 16, part 3. So we're discussing how to select the best model. Okay, so we talked about the steps in selecting the best model, specifying the maximal model, choosing a criteria for selecting the model or selecting the variables in the model, and a strategy, and that's where we are now. We've talked about the all possible regressions, where you do all possible regressions, and that guarantees that you will see the best model of all of them. But sometimes that's prohibitive because of time or effort or computer power. Then we've talked about backwards elimination. We start with a full model, and then we eliminate or remove any variables from the model that are above our threshold. And a good threshold is usually 0.1 in that case. And then forward selection is where we take and we start with nothing in the model, a zero-based model or null model, and then we look at, we choose the single variable that has the lowest p-value of all the variables in the pool of selector or predictor variables. And then once we've chosen the first variable, it stays in the model no matter what, and we then do the partial f-test for any other variables, a variables added in order type of test here. So that's what we're doing there. So let's look at an example here that I've made up. Let's say we've got three variables, x1, x2, and x3, and by themselves, single variable models, we have p-values of 0.02, 0.1, and 0.08. Okay, so all three start out as significant. All right, and that would be an ideal case where at least 0.1 or lower. So step one, we would select x1 because it has the lowest p-value. Step two would be that we are calculating these partial f statistics for x2 and x3. And let's say that we end up with 0.11 and 0.09. So x3 has a partial f statistic with significance of 0.09, which is less than our cutoff of 0.1. So we are going to add x3 to our model. Okay? And so now let's say we look at this model, and our model would be beta 1 plus, I should say a 3 here, beta 1 x1, beta 3 x3 plus beta naught plus epsilon. And let's say we look at the model, and now we see that once we added x3 to the model, the p-value for x1 has increased to 0.18 above our threshold. Well, it doesn't matter with forward selection. We're going to keep it in there. And then we'll look to see if we should select x2. And so we would calculate then f of x2 given x1 and x3. And if that p-value is less than 0.1, then we would add it. If not, then we would not. Let's say that this has a p-value of let's see, we already have, so this would be x2, and let's say it has a p-value of 0.31, and so we would stop and not add it to our model. Okay, so as you can see, this situation here would make someone think that maybe the forward selection is not the best selection strategy. And so that's what we're going to talk about next, is the stepwise selection process, okay? And then we'll talk about conducting the analysis and evaluating reliability. Okay. And the next time we will talk about the example. All right. So let's get started. We have the stepwise regression procedure, and it's a version of the forward selection. Is a version of the forward selection procedure, but it re-examines any variables that are already in the model to see if they have violated our selection criteria. And so SAS has a default of 0.15, both for entering the variable into the model and for the criteria for removing a variable from the model or kicking it out. Okay, so Now let's look at the stepwise procedure for our example. Now I'm going to go back to here, and I want to show you and remind you for x1 we had a, let's see, I don't see the p-value here. Do we have the p-value? So that's r squared. Oh yes, so here we go. So for height, age, and age squared here, we have p-values of 0.03, 0.71, and 0.923, okay? So those are our single variable models. And obviously we would choose x1 here into the model. Okay, so we choose x1, and here's the f value, and the p value was what, 0.03, I believe. And now we look at step 2, and let's see, so step 2, we look at, let's see if I can find it. So step 1H, okay, so step 2, here we go. We're going to look at age, adding age and age squared into the model. And we look at the p-value, and we've got here 0.05 or 0.06, 0.057, let's say, for that, and 0.06. So this was, 0.057, and so we added x2 to the model, okay? And then when we look at the third step here, we see that, now I want to point out again that up here, age squared was significant. It was fairly significant, 0.0565, is that right? Yeah, that's age, I'm sorry, not age squared. So when we look up here, age squared 0.0614 was the p-value. But after we add age to the model, then the p-value here for age squared added to the model with x1 and x2 skyrockets up to 0.92. So very high, okay? So it definitely changes the value. And so x3 had a p-value of 0.92. Okay. So we're ending up with the same variable. A lot of times you will end up with the same model whether you choose forward, backwards, or stepwise. But then there's those few times where you will end up with a drastically different model choosing stepwise than you did with forward or backward selection. And so it's those times that you may want to use the stepwise, but you don't know when that is. But in R, it's very easy to run all three of these, and unless you have a whole lot of variables, it's also very fast, okay? In fact, I'd say my experience is that it's faster in R than it is in SAS, okay? So with this having a p-value of 0.92, and this was for f, not p, f of x3 given x1 and x2, that was the partial f test that we calculated. We have a p-value of 0.92. We would not add it in there. It exceeds our limit of 0.15. And once we have both in the model, let's see if we can see the model with them in there. With both variables in the model, it's over here. We see that height has a 0.0013 and age has a 0.0565 p-value. So both are less than 0.15, so we do not remove them from the model. Okay. And they've repeated it here, but just adding x3, the f value here, but not the p-value, which was what, 0.92. Okay. So this has a 0.0013 now, and this has a now I've forgotten, 0.056. Yep. Oops. Okay. So they're definitely below the 0.15 cutoff. Okay. So now that we've talked about the four different selection methods or strategies, let's talk about conducting the analysis. Okay, so this is step 4. And so we want to use our diagnostic methods from chapter 14. If you remember when I first went over the introduction to this chapter, I said, oh, it looks like they forgot chapter 14, the diagnostics, but they actually meant that by conducting the analysis that they would include the diagnostics, because really you've already done the analysis when you do the forward and or backwards or stepwise selection. It gives you all of the coefficients and significance and all that. So really the only thing left to do for that part is analyzing the diagnostics. So that's good. Now, the next thing that you want to do is you want to test the reliability of your analysis. And so what we're going to do is we're going to take and consider the sample that we have like it's a population. We want to pretend like it's a population, and we're going to take a random sample out of that the sample that we've taken, and this is only good for larger samples. This does not work on small samples. And we're going to randomly select about half for what we call a training or building set. And what we normally do is we normally have this training sample or build sample, and we use it to select the model, okay? And so what we do, so that's one way to do it. But this is a different, and so that's called a validation or sensitivity test. So what we're doing with the book here is a different method. There are many methods here. One is called cross-validation, and you can use different, what we call folds. So we might partition the data into 10 different folds and then calculate it based on, calculate things or measures based on each of those folds, if you will, and then compare those and average them and compare those to the original, and we can see how much or little variation there is between the values based on those different samples. So what we're going to do here is we're going to partition the data. We're going to randomly select half the data for our training data set. And then the remaining half will be our validation or holdout sample. And so N1 is the sample size for our training data set, and N2 is the sample size for our validation. So we're going to introduce something, we're going to tweak R squared to account for this. So what we're doing is, this is prediction error, is this quantity here. So there's a little problem with subscripts there, but that's okay. So remember that R squared is equal to 1 minus, I've left out the 1 minus SSE over SSY. And so we're going to replace SSE with the prediction error. Now, remember that from I equals 1 up to N1, this is our training data. And then from N1 plus 1 up to N2 is going to be our validation. And so what we do is we're going to only put this measurement here on the validation data set. So we're going to calculate R squared for, well, actually we're going to do it for both of these. So we're going to calculate the R squared using the training data set and R squared using the validation data set. And we're going to take the difference between these, and we call this the shrinkage, okay? And so if the shrinkage is less than 0.1, then the model is considered reliable, all right? And if it's not considered reliable. So So what we've done is for this we've got I equals n1 plus 1 up to n2. And we take yi minus yi hat quantity squared. And so we've got some examples of prediction error. And so this would be a bad example where it oscillates around the line, fitted line. This is a poor example, or example of poor prediction error because it goes down and then up, and it's not around a straight line. This one oscillates as well, and this would be a case of good prediction error where it oscillates around the fitted line, and that is in a random-like manner. Okay. So let's talk about an example of data. So this is a data set by Lewis and Taylor in 1967. The response variable is weight. We have height, age, and sex. And we're going to choose a maximum model, and boy, are we going to add some things to this. So we have the basic predictors that are listed above, height, age, and sex. We're also going to include quadratic terms, that means the squared terms. And we're going to include cubic terms. And this is for age and height only. And then we're going to include interaction terms for sex with each power of age and height. We're going to have 13 predictor variables for weight. So let's look at what they are. They're age squared, age cubed, height squared, height cubed, and sex. And then we have sex with age squared, sex by age cubed, sex by height squared, and sex by height cubed. So take a look at this wording and make sure that you see how that means this. Now, we're going to try to include a selection criteria. So they've decided to use Mallow's C and also look at R squared, and we're going to see why in just a minute. So we need to include a strategy or select a strategy, and we're going to use backward elimination procedure. Okay, so this is important to remember that we're using backwards elimination, and so we're starting out with everything in the model, and then we're going to look at this. Okay, so we also need to evaluate reliability, so we randomly partition the data into two data sets. Data set 1 is the training, and data set 2 is the validation, and we see that there's 118 and 119, so as close to equal as we could get with the odd value of 237. Okay, so let's look at the analysis of data set 1. Okay, and so what we're going to do, and these are just descriptive statistics, but I want to point out that what they've done is they've subtracted the mean from age, and they subtracted the height, the mean of the height from height, and here are the mean values. And what this does is this makes the average of age 0 and the average of height 0. Okay, so again, this is called centering the variable, and so we take x minus x bar, and that gives you a mean, an adjusted mean, if you will, of 0. Okay, so we can see that the min, the max, the standard deviation, and of the weight, age, the age subtracted from the centered age and the centered mean. That's the or height. That's the easiest way to say it. Now, here's a correlation matrix that I really don't like because they've done away with the decimal places. They've multiplied everything by 100. So the 59 here is really R is equal to 0.59. So for someone like me who knows what this means, that's okay, but for students, I really don't like using this. But the other thing they didn't do was give us labels for the other axis, or for the, yeah. So they've done something a little different. Instead of having a diagonal of 1s, they've avoided that diagonal by giving us a lower diagonal matrix, and they've offset everything by 1. So you'll notice that there's no row up here for height. It's missing. Or weight, I'm sorry. But they do have weight up here. And so you only have, on the horizontal, you only have through here, you have those variables. And on the vertical here, we have these without the weight. And so that gives us a matrix that doesn't have those ones across the diagonal, and yet we still have every correlation coefficient that we want. Okay. Now, what I did was I went through and I circled in purple any of those values that were 0.8 or above, because those are potentials for collinearity. And so I've got height times I'll start at the bottom, height times sex times height cubed, and I go over and I see a 0.88 with height cubed. Well, this makes perfect sense that sex times height cubed is highly correlated with height cubed. No surprise there. And then we have, I went up too far. How about sex times height, and that's going to be with height. Yes, that makes sense. And then the next one, sex by age cubed, and that's going to be correlated with sex by age. That, again, makes sense. And then finally, we've got age cubed with age squared. They're highly correlated. So this implies that you would want to maybe remove, if one of these is if some of these are selected, you don't want to keep all of them in there because of the collinearity. Okay. So remember that the CP for the max model is always going to be P plus 1. Here is P, so 14 is exactly P plus 1, which is what we said would happen, and it did. And so with all 13, here is a backward selection and just throwing everything in there and just saying, do a backward selection by removing whichever one has the highest p-value above 0.1. And so, so this is the variables. It says variables used, but there's 13 variables in here, so that that doesn't really make much sense to me. But okay, so we have 13, and then height 3, backward selection based on data set 1. So height 3, and all right, so that only has height cubed there, and then so we look down and we see that that's exactly 14, and we look through these and we're looking first at the CP, so Mallows C, and when we look at model 3 here, okay, model 3 says it has height and sex, and it's the interaction of height and sex, and negative 0.12 is not very close to 3 plus 1, which is 4. And again, negative 0.82 is not very close to 6, P plus 1 there. Okay, so those are not very good models looking at our CP here. And so let's see what the book says. They say we've got 14 in the first row, and CP of 12 in the second row is from the model with height cubed. And so this is the least significant variable. So height cubed is removed. So when it says used, this should say variable removed. Okay, that makes more sense. It's what I thought it was before, and then I didn't read the table carefully. Okay, so this table doesn't suggest the best model, because there's several possibilities. We may choose a model with 2 variables, height and age, cubed, based on, so the second row, height cubed, yeah, okay, 12. Okay, so it says the second row is from the model with height cubed, least significant variable removed. So we're removing the variable above it. Okay, so so this is the model with 12 in it, and height, has been removed from the model, height cubed. Okay, that makes sense. And so we may choose a model with 2 variables, height and age cubed. So let's look at height and age cubed. And I see height cubed, but I don't see height and age cubed. Okay, so here, right here. Okay, so this would be this model here. I believe. But this model doesn't follow all the lower term of the convention. Okay, so we may choose a model with two variables, and that would be, yes, this one, because it has two variables in it. P is 2. And the problem is we'd have age cubed and height, but we don't have age squared or age. And anytime we choose a higher order variable, the convention is that we have all the lower order of that variable in there as well, so that we have the full, if you have a polynomial, you have the full polynomial, not just one term of it, okay? And so we haven't chosen any lower order terms. So we're going to look at two different ways of doing this: interaction ordering and power ordering. So the first is the interaction ordering, okay? So again, this is backward selection. So what we're doing is we're looking at so this is interaction ordered, fitting based on data set 1 again. So remember, it's called a training data set, so we do the selection on that training data set, and then we fit that model to the validation data set, and we see the difference, that shrinkage in R squared. Okay, so here this would be removed, I guess, is a way to say we're removing this one here in backward selection. So so we look down through here and we say, okay, so we have these interactions, and it's ordered. It said first interaction ordering and power ordering. Okay. Yep. Okay, so this one just says interaction ordering. So we look at, there's interactions here. These are the first ones to be removed, are the interactions, and based on that, and interesting that sex and age are down here. So I would have thought that they would be up there. Okay, so but we have these interactions, and if we remove them, we can still have the age cubed. So here's the cubed, here's the squared. Okay, so that's what we're doing. We're taking the higher orders. It doesn't tell us, but it's ordered by the interaction and then by the order of the polynomial, okay? The power of the polynomial. And so I guess I shouldn't say power with statistics, it's the exponent. All right. So we remove those first, and we see how, of course, with the full model, 14, and then we drop down to 12, and P plus 1, remember, is 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, and 2. Okay, so that's the P plus 1. And we see that, let's see, so we see that this is pretty close to 6. But we're looking for the lower one. And you notice that what happens is it keeps going down until there, and then it goes back up, increases. Okay? So this is the minimum value. So that makes us look at this model with 4 values. It's the smallest CP, and it's not too far from 5, our P plus 1. Okay? And what this is it would have these variables in there: height, age, sex, and sex interacted with height. Okay? And so this would be, using this method, this would be the best model that we could choose with these 4 variables. Okay? And when we look at this, we have a decrease. It's talking about from the one before, from 0.626 to 625. And so if we look at this, this is about 0.626 and 0.625. So we don't have much of a difference in the R squared. Remember, we're looking at CP primarily, but we're also looking at R squared as kind of a secondary or second opinion. All right. Now, let's look at this power-ordered fitting. And so what this is we're ordered by, does it tell me? Okay, but this is ordered by power, interaction, and power. You'll see. So first by interaction, and then, or by power, and then by interaction, and then we have, then we have by the cube terms, then the squared terms, and then the individual terms. Okay. And so we're looking at this CP, and it's getting smaller and smaller. Oops, here's one that gets small, but that's a little far away from 10. That's about 3 away. 9, 8, 7, 6, 5, 4, 3, and 2. And this is not too far. This is a little over 1, not too far from 6. But this one here, this is small, but it's pretty far away from 8. So we're looking at the smallest ones that we can, and it's pretty far away from 8. This one is pretty close to 4 as well. Okay, so it says closer to expected value with 2 less predictors than this model here with 7. Okay, let me undo some of this to try to take out some of the mess. Okay, so we can see what we've written. And so when we look at this one here, this r squared in this model is also bigger than we had up here in this model. 625 was about it, and this is 627. Okay, so a little bit bigger. Okay, so we eliminate all interaction terms first by power and then by polynomials. Okay, so here is what we did, just as I said earlier, I hope. So let's see the analysis. A model of size p equals 5 gives the smallest CP, which is not too far away from p plus 1. Okay, because I was about to say 4.77 is smaller, but not by much. And there is a decrease in r squared from 0.633 here to 0.627. That's not a very big decrease. And so the best model in this, using this method, has, we said, was here. So it has 5 variables in it. So height, age, sex, height squared, and age squared. Okay, so that would be our model there. And so we now have 2 possible models, and we can choose the second model since it has a slightly larger r squared value. Now, what I want to say is, yes, that is true, but remember that the other thing we're looking for is parsimony. And this model here is before model 1 might be the one we choose because it has 1 less variable in it. And it doesn't violate anything as far as the powers or interaction here, because we have height, age, sex, and then we have sex times height. That is acceptable as a model. Okay, and so it doesn't include any squared terms. That also is advantageous. I find that advantageous because explaining why you have a squared term in something is sometimes difficult to explain. Okay. So that's it for this video. Please don't forget to scan your lecture notes by midnight, the date listed in the course calendar. If you have questions, come to virtual office hours. If you can't make it to virtual office hours before you require an answer, then by all means email me, but please send me a picture of the problem because I may not have it available, and a picture of your work so far so I can see how you're approaching the problem, and that will help me help you efficiently and quickly. Please take care of yourself, and we hope to see you next time.